Welcome back. It's my pleasure to introduce Miranda, and she will talk to us about which physical systems can be quantized.
Good morning, everyone. It's a great pleasure to be here and surrounded by the role models I had. And well, it's a pity that Jonathan will connect online today, unfortunately. And Lisa too? Oh, okay, and everyone is very scared because of the email that Peter sent. Okay, so good. Okay, I'm going too quick. Okay, so what's in this talk? I want to explain two stories. In the stories, there will be Hamiltonian group actions and quantizations, and there will be, of course, symplectic geometry. But there will also be some other geometries that will let us answer the title, what systems can be quantized? And the story one starts here a while ago, in 2001. I was attending a conference here organized by Lisa, and as you can see, Yael and Jonathan were speakers, and many of you here were speakers. For me, it was fantastic to see that all these people that I had been reading their papers really existed, and it was like an important moment in my life. I remember this conference. Also, Lisa prepared a very nice letter of invitation where it says that I got 1,000 Canadian dollars, and this created some problem in the entry. Whenever I enter Canada, they remember that maybe. Okay, so of course the main characters of story one are Lisa, Yael, and Jonathan, who at that moment already, by 2001, they had already amazing papers that I had tried to follow and understand, okay? And Jonathan, even he wrote a paper as an undergraduate on divisibility by primes. And they have been collaborating among them. It's fantastic to see not only their own production, but they have been collaborating, and among their papers, there is paper with Yael and Jonathan, and there is many papers with Lisa and Jonathan as author. One of them is geometric quantization and Witten's semi-classical manifolds invariant, which leads me to story two, which is to look at quantization from the perspective of topological quantum field theory. So I'm going to start with, I'm going to present to you now the characters of story two. I presented the characters of story one.
On the 12th of January 1992, the merchant ship Old Susan, sailing the Hong Kong-San Diego line, was caught in a terrible storm and lost all its cargo. More than 20,000 rubber ducks. "14 years and 6,000 miles later, the inhabitants of Stratford in Scotland woke up to the unusual sight of thousands of ducks invading their coastline. Life is full of surprising endings.
Yeah, so when I got this invitation, Jonathan told me, I want you to talk about the ducks. I said, no, but I want to talk about quantization. How are we gonna do it? So the main characters of this story too are 29,000 rubber ducks lost in the ocean. And there is math behind this, and I'm going to explain it. But of course, well, this is an advertisement. They want you to buy the car. And of course, life is full of surprising endings, which the sentence has to do with the fact that the trajectories of some fluid paths are undecidable. And this has led two of my collaborators, Jose Ángel González Prieto and Daniel Peralta Salas, to construct a computer, which is a hybrid between fluid and quantum. And this is what I will explain towards the end of my talk. And this can be understood as a quantization tool. as a topological quantum field theory. So these are the characters of the second one. I mean, it's an ambitious talk. I'm doing this because Jonathan asked me to do, and whatever Jonathan asked me to do, I do. So, okay. It's good that after we can drink some coffee. So the story of the 29,000 rubber ducks, indeed, it's based on a true story. In '92, there was a cargo that lost the rubber ducks, okay? And there have been people who have been following and tracking the path of these ducks, you know? There are many people in the world, and some people like to do this. So they have been tracking the ducks, and indeed, they even have been using, as I will show in the next slide, a simulator to find them. But these ducks escaped all the forecast given by this simulator, these numerical simulations. So in particular, in November, 10 rubber ducks appeared in Sitka, and then many years later, in 2007, the advertisement says that they were expected to arrive in the British shores. And this is what The Guardian was telling us. They were saying thousands of rubber ducks to land on the British shore. But the truth is that just one of them showed up and decided to do it in Scotland. Why? Okay. So what I'm going to explain, well, I mean, here is the story of these simulators. And indeed, there is a funny story. These people have been tracking all kinds of flotsam, like the rubber ducks, like Nikes. They have been making an experiment, throwing bottles with messages inside these bottles. Remember these old films where you have love messages in the bottles? What do you want to do this? Only 2% of the bottles are going to be recovered, and probably half of them will give you a rejection to this proposal that you sent inside the bottle. So please don't do it, okay? Also, it's not very nice to throw things to the ocean. So they had been doing this experiment, and how do they know that only 2% of the messages were recovered? Because they had been putting a message saying that this is $50, that you get $50 if you tell them that you got these bottles, so it's quite accurate. So, but what is quantization, and what does the rubber ducks have to do with quantization? Well, that's a summary of the talk of Mark yesterday, indeed. Mark explained us this idea of quantization, like we want to translate some classical into quantum information, and the truth is that we still don't understand very well how it works. So this comic is telling us exactly, right? You go there, you have been all your life trying to do it, and if there is an afterlife, you get up there, and they don't let you in because they say you still don't understand quantum theory, right? So what is as we saw yesterday in the talk of Mark, the idea is that we want to translate some classical systems with some observables, which are Hamiltonian systems, and a bracket, into quantum system with operators and commutators. And as Mark pointed out yesterday, very important fact is that it's already to construct the representation is hard, and in most cases we still don't know how to construct these operators and see if things work. So I'm going to remind you very quickly what Mark explained, not about Keller quantization, but about the quantization that uses a real polarization. So a Lagrangian foliation on your actual manifold. Okay, so remember, as we saw yesterday, we need a prequantum system. So we need a symplectic manifold with an integral class of the symplectic form, okay? And then we take a complex line bundle with a connection with curvature, this form, okay? And then, well, as we discussed yesterday, integrable systems provide natural examples of real polarization. However, as Mark observed, that singularities can be a problem. And we consider the flat sections equation, okay? The flat sections equation, which is this one. Oh, this is working or not? This doesn't seem to work. Well, I don't dare to touch this because this is connected. No, this is not going to work. So in any case, we have the flat sections equation there, okay? And as Mark observed, this doesn't have a solution, but we can look for which which leaves of the polarization of the foliation admit a global section, and these are called the Bohr-Sommerfeld leaves. And this is a computation that we saw yesterday, okay? And as observed by Mark, because of Arnold-Liouville theorem, this is a model of polarizations for integrable systems in the regular case. And then, as a take-home message, if we have to say this very quickly, and we consider toric manifolds, geometric quantization can be read from the polytope. How? Essentially by looking at the integral points of the lattice, and that's, there have been several people in this room who have been working on this. Maybe the first people who observed this in this direction were Victor Guillemin and Shlomo Stenberg, who identified the Bohr-Sommerfeld leaves with the integral points on the Dalsan polytope, and in a way, we give a definition, Sniatyski gave a definition of quantization that counts exactly the Bohr-Sommerfeld leaves. And indeed, this is what Mark had done in his thesis, Mark Hamilton. He proved that quantization is really given by the count of Bohr-Sommerfeld leaves in the interior. And then there are many questions about what happens with the singularities, which Mark has been working a long time. So the message is that in symplectic geometry, it's possible to quantize in the case in which we have an additional torus action, and a toric manifold, by counting the integral points of the lattice, and these points are identified with Bohr-Sommerfeld leaves. So we have a beautiful picture. And of course, I had to, Jonathan told me talk about the ducks, but I said, okay, this is your birthday, so I should be talking about something with it together. He said, okay, but just a little bit. So I'm following his advice, of course. As I said, I always do whatever he tells me to do. So I'm going to explain something we did in extending this picture when we have symplectic manifolds with some singularities. And I'm going to try to explain what are these singular symplectic manifolds. Okay? Some singular symplectic manifolds are these folded symplectic manifolds on which many people have been working on. But the way to introduce them is to think in the following way. I'm going to take an hypersurface of my manifold, okay? And I'm going to consider, I'm not going to talk about Poisson geometry. I could look at this from the Poisson geometry perspective, but I'm going to avoid it because I need to talk about the ducks. And I'm going to consider vector fields which along this critical hypersurface are tangent to this hypersurface, okay? And the question now is, do I have a bundle, a vector bundle, such that the sections are precisely given by these vectors? This looks a very strange question, but it's a very natural question for algebraic geometers. Indeed, Serre already observed that when you have a C-infinity module, which is free and finally generated, okay? Well, he observed this in the algebraic case, but you can also do it in the analytic case and in the smooth case. If you have a module which is free and finally generated, then you have a vector bundle such that these vector fields are sections of this bundle, okay? And in the case in which I consider a regular hypersurface, then this bundle is called the B tangent bundle. And why B? B could come from Barcelona, but it's not the case. B comes from boundary, because originally it was Richard Melrose who had been working with these objects when trying to give a proof of the Atiyah-Patodi-Singer theorem, which follow exactly the same proof of Atiyah-Singer, just changing the forms, okay? And then he introduced all this language of B calculus. So B comes from boundary, and essentially in the case of Melrose, well, this hypersurface is just the boundary, okay? But then you can double your manifold and it gets a regular hypersurface. So essentially, this language of B tangent bundles is good to deal also with the hypersurface situation. So why do I do this? Because if I have I can identify these vector fields as sections of a bundle, then I can do calculus. What do I mean by that? Well, first of all, I can define what is a form. How do I do it? Well, first I just dualize. I define what is the B cotangent bundle and I do it in the most easy possible situation. I just take the B tangent bundle and I dualize. And once I have this, I can define one forms as sections of this bundle. Okay? And I can define any kind of forms as sections of the exterior product of this bundle. And in this way, I can define what is called B forms. This was done by Melrose. I'm just following what he did. And what's interesting to observe, in the case in which I have a regular hypersurface, then assume that that this regular hypersurface has equation z equal to 0. Then we can easily decompose any B form can be expressed in terms of the RAM form, because we can always decompose in this way. And here I have a form which is not smooth. This z over z is not smooth as the RAM form, but is smooth as a section of the B cotangent bundle. And that's a little bit the deal. So what is a singular symplectic structure that we call B symplectic structure is just a symplectic structure, but taking as forms a B form. So a B symplectic form is just a closed non-degenerate B form of degree 2. And this is more general than symplectic structures because I can have these singularities. Okay, for instance, I could take sphere, okay, and I take as coordinates the height and theta, and then I could take as form. This would be an example of singular form. Okay, so we want to quantize these manifolds. Okay, and the definition of B symplectic form is like that. Of course, it's a Poisson structure. I have to say it, but I'm completely avoiding the Poisson definition, the Poisson side of the story here. And why do we care about singular structures? Do you have natural examples that justify that we deal with them? Well, yes, indeed, we know that if we consider geodesics or Riemannian manifolds, these look like a tangent bundle. So they are indeed the set of geodesics on a Riemannian manifold has indeed a symplectic structure. And what happens if we consider a pseudo-Riemannian manifold? Then what happens is that this is no longer symplectic. What happens is that if we take a pseudo-Riemannian manifold and we take the space of all oriented non-parametrized geodesics, I would like this to work, but it doesn't. Okay. Then we consider this set of geodesics as splits as the set of space-like geodesics, time-like geodesics, and light-like geodesics. Okay? And what happens is that the space-like and time-like geodesics are indeed symplectic. Okay? Are indeed symplectic. But what happens when I'm on light-like geodesics? This set is no longer symplectic, and indeed this set has a contact structure. And in dimension 2, this set, I can look at the whole set of geodesics, and I can describe this as a B-symplectic structure. Okay, so, sorry? Yeah, it's a submanifold. It's a contact, indeed, in general, in any dimension, it's a contact submanifold. And in dimension, if I consider the Lorentz plane, then dimension is 1, and it's the same. It's co-symplectic and contact. Okay, and then the whole, if I consider the set of all geodesics, this is B-symplectic. This example is taken from a paper by Sergei Tabasnikov and Boris Hessin. Okay, so it's quite natural. We have examples of this, and I'm going to give you another example, which is the restricted three-body problem. So we know the three-body problem is complicated, right? When we want to determine the trajectory of a satellite. Yeah, the pointer is not cooperating. Do you see it? No, just the pointer. Yeah. Are you using your laptop? Yeah, I'm using my own laptop, but it's connected to my laptop.
I don't know, I've never had that before.
Okay.
Put you a laser, is that?
Okay, thank you. Yeah, I can use both. Okay. So if we have, so we want to determine the trajectory of a spacecraft, right? And well, in principle, this should be a very complicated problem if we think that this is the three-body problem, because this is not integrable. However, the models that are usually used in this case is what is called the restricted three-body problem, which is a simplification of the three-body problem. This simplification consists of two main facts. First, we assume that in all time, the three bodies are going to be on the same plane. So this is a planar problem. And secondly, we assume that the spacecraft doesn't have mass that makes the primary, and this could be the Earth and the Moon, okay? Thank you. You also need to plug this? Okay, fantastic. Okay, great, thank you. Great. So now the spacecraft, if the spacecraft doesn't have mass, or we assume that it's negligible, then will not exert attraction on the Earth and the Moon, okay? However, these two guys are attracted to each other. So in a way, if this spacecraft was not here, this would be a two-body problem, like the Kepler problem, okay? And then the trajectories would be either circular, elliptic, or parabolic, so we assume that they are circular to have full symmetry. So these are the two restrictions. Well, three, indeed. We assume that the spacecraft doesn't have, that has negligible mass in this story, that the three bodies move on a plane, okay? And we assume that these two guys, which determine a Kepler problem, indeed the solutions are circular. So, good. And this model, indeed, it's used by NASA, indeed, to do computation. So it's good that we understand it properly. People in dynamical systems have been working with this problem, and usually, I mean, there are equations. Give me equations. I give you equations. Of course, this is a Hamiltonian system, okay? The total energy of the system is the sum of the kinetic and the potential energy, and this is the expression of the potential energy. Of course, I don't expect you to follow all the computations, but I want to show you these computations exist. Okay, we have normalized here the mass. And this is a Hamiltonian system, and people who are working with this problem, first they consider a change to polar coordinates because this is the circular problem. And secondly, they use what is called McGehee coordinates. McGehee coordinates are coordinates that send to infinity the zero, and this is convenient because we may have the satellite that escapes the radar, and in this situation, this is what they call it goes to infinity, okay? And in this situation, it's convenient to perform this change of coordinates. And this is what the people in dynamical systems and people working with these equations on NASA use. But however, when they have this, they say, oh, away from x equal to 0, this is a symplectic problem. What happens when x is 0? What happens is that we just do the pullback and we get a form that is one of our singular forms. Okay, here we have a power, it's power 3, so it's not really a B form, it's a B3 form, okay? So it's interesting to understand, right? Because understanding, this is a model that we use for real life. So it seems that bisymplectic geometry can be useful here. So this justifies, okay? So a summary why we care about this. Well, here is the summary, but the most important thing is the pictures of the people. So everyone is smiling here. So this means this is a good place to be working on. Okay, so we have Victor smiling here, me with Anarita a long time ago in Paris, enjoying some crepes, smiling. This is a former student of mine who happened after she left, after doing the PhD, okay, she defended the PhD, she got a gold medal in cycling in Tokyo. So this is why she's known for. But on her Wikipedia page, she has like doctoral advisor Eva Miranda. I feel so proud. So she's also smiling, of course. Well, I don't know, maybe because of bisymplectic geometry, maybe because of the gold medal. And of course, Jonathan smiling here, Melrose smiling, Richard Ness, not easy to get him smiling, he's smiling. And here we have Cedric Combs, former student of mine, smiling. So this is a good reason to work with these objects. Of course, bisymplectic geometry also models manifolds with boundary. So of course, this is relevant for many, many different things. And also they appear in pi-level equations, etc. So there are reasons to study these objects. And there are reasons also to quantize these objects. So now I'm going to try to do the exercise that Mark did yesterday with the same definitions, but applied to B-symplectic objects. Okay, so if I do this, well, first of all, in order to consider Hamiltonian actions, if I think, if I take the classical definition of Hamiltonian, I'm going to lose a lot of information, because then, for instance, a toric action, I would never be able to have a toric action, if you think about it. So I need to increase the box of potential Hamiltonians. I need to add some functions that look totally forbidden, which are combinations of constant if z is the equation that gives me the singularity of this sort, plus some smooth function. And if I include this, then I get a Hamiltonian that is going to be tangent, a Hamiltonian vector field that is going to be tangent to this set, okay? And it wouldn't be observed otherwise. So in order to have toric B-symplectic manifolds, I need to enlarge the set of Hamiltonians. And then I could try to mimic exactly what Mark did yesterday, okay? So if I consider, for instance, a toric action, then the orbits would be give me examples of Lagrangian polarization, okay? With Anarita, one of the things we were doing in Paris, other than eating that fantastic crepe, was proving Adelson theorem for this B manifold. So we have the Adelson theorem, so we can try to make things work, okay? And indeed, we can even make a picture of, well, now I'm confused with some, oh, now it worked. Now I don't need this one, okay. I don't need to have enough of one. Okay, so I went too quick. This would be an example. This is exactly what I was trying to draw here, but much better. This would be an example of Hamiltonian action, of toric action on the case of the B sphere, okay? And I would also have this. Oh no, it doesn't work. Does it work? No, I need it. Oh yeah, it works, but it's very slow. Okay, and in the case of the torus, I can also cook up, as you can see here, a B form, and I cook up a moment map, okay? And well, there are things that we don't like, right? Initially, it looks like the image of the moment map is not going to be a polytope, but we can arrange to be a polytope by doing the adequate identifications, which I will not talk about today because I'm not here to talk about the Adelson theorem. I'm here to talk about the DAX. Okay, so this is well, I'm going to keep on playing with the two ones. So this is a picture. If I want to make a picture of what would be the Bohr-Sommerfeld leaves in the case of the B sphere, I get an interesting phenomenon. I can compute it, and I get infinite number of Bohr-Sommerfeld leaves. Of course, if you want to define quantization as the Bohr-Sommerfeld leaves, we have a problem, because if something is compact, we expect to have a quantization model which is finite. But okay, here I chose red, okay? Red, the ones that on the up hemisphere, on the northern hemisphere, and in blue, the ones on the southern hemisphere. These are the colors of Barça 2, okay? My team. But what is interesting is that there is a kind of cancellation phenomena close to here, because the orientation, because the B-symplectic form explodes, the form here, when we go to h equal to 0 explodes, and there is a change of the sign on the volume when we cross this hypersurface. This justifies that there is a kind of cancellation of infinity, and therefore, at the end of the day, even if it doesn't look like this, we can assign, if you want to assign, according to the color, to these Bohr-Sommerfeld leaves, and the total sum is finite. But this would be more or less the intuition. How do you justify this? Well, you can justify this using the machinery of formal quantization It's very good that on the first day, Reyer already introduced many things. In particular, he talked about formal quantization. So I can use it very quickly. So formal quantization was introduced by many people, and I'm forgetting names. Miranda, Paradan, Bern, and Jonathan Weizmann too. And essentially, it uses the idea that we are giving a definition of quantization that we want to satisfy the principle of quantization commutes with reduction. Okay? So indeed, the idea is that we have, well, a pre-quantum system, okay, and by twisting by an operator, we have an elliptic operator, and the quantization is the index of this operator. And we think of this as a virtual vector space. That's formal quantization. Yeah.
And some people would call this Dirac-Dolbeau.
Okay. Dirac-Dolbeau, yeah. Dirac-Dolbeau, well, I call it formal, but I agree. Yeah. Okay, good. Now, what happens if M is non-compact? And this is something on which Jonathan has been working on, and indeed it was one of the papers I chose under his picture. He did this before 2001, okay? Which is to describe a method for quantizing the non-compact situation, and there you need to assume that the moment map is proper. So the idea was to apply this idea of Jonathan also to B-symplectic manifolds. And, well, essentially the trick is that you define, this is very long, but essentially you define quantization, okay? You want to define quantization as the pieces associated to each weight, okay? And then, because you assume that quantization commutes with reduction, because your definition indeed is such that quantization commutes with reduction, you end up having this formula. So you need to reduce, and you need to take the quantization of the reduction. Okay, and then this is compact, therefore you have a good definition. Indeed, this definition was the abstract definition given by Jonathan, and then Mark Braverman and Paul-Émile Paradan proved that indeed this quantization is the index of an operator. So in the big case, we use this idea, and well, first we proved with Victor and Jonathan. Somebody's talking?
I don't know.
Okay. Lisa, do you have a question? No. Okay. So with Victor and Jonathan, we proved that this is finite dimensional, and then with Jonathan, we understood what is the relation between this quantization and the computation of Bohr-Sommerfeld leaves, indeed, because if you consider a torus action, okay, and you take into account the sign that comes from the change of orientation, then quantization is given by this formula. In the case in which you have a toric action, then these quotients are just points. So indeed what you are doing with these quotients, these are just the points, and these are identified with the integral points on the lattice, right? So indeed, the formal quantization of a toric B-symplectic manifold coincides with the count of Bohr-Sommerfeld leaves with sign, okay? And indeed, can you identify this quantization indeed as an index of an operator? The answer is yes, and this was proved by Braverman, Loisides, and Song. So this is the end of story one. Oh my God, and I have how many minutes? I have 17 minutes, no? Who is my chairman? You are my chairman, Peter? Great, okay. So I have 17 minutes to tell the story of the ducks. I'm very happy because I'm going to be able to do it. So Jonathan will be happy. Yeah.
Not to take out of your time.
You are doing that.
Quick question about your sphere with the blue and red circles.
Yeah.
Just really naively for the picture, it looks like they would all cancel each other out.
Exactly. Exactly. They are going to. Yeah. The thing is that that's the intuition. The intuition is that they are okay. That's very good. If we go back to this picture of understanding the integral point also as understanding the Bohr-Sommerfeld leaf such that they leave integral area, okay, then in this picture they would cancel out somehow. But in another picture, This is what I think she was meaning. If we move down this here, then the areas are not going to be the same, so they are not going to cancel out. But the important thing is that the total sum will be finite. So very good. This picture was too symmetrical. It would be 0. Nice. Okay, let's go back. Now it's when I have to, jump and talk about topological quantum field theory. And I was like 3 days thinking how to do this. I'm not exaggerating, 3 days thinking how to do this. And my conclusion was that it's very hard to explain how you can get, there are many examples. So topological quantum field theory has a beginning, and there are many examples where you can connect it to geometric quantization. For instance, the case, that paper that I point to of Lisa and Jonathan. But a good summary of this would be this conversation with Dirac and Feynman. Dirac would tell to Feynman, I have an equation, do you have one too? So I have an equation would be the classical quantization, and you don't have equations, but you have hand waving, maybe it would be the topological quantum field theory. Maybe this is unfair, but this is my summary of how we jump from one to the other. So the idea is that with the models of topological quantum field theory, in some cases, we can recover classical quantization. And now I want to present a model of topological quantum field theory that explains the DACs, but this is the paper of Jonathan and Lisa I was talking about, where they give an interpretation of the Witten-Reshetnikoff-Turaev invariants for 3 manifolds from quantization perspective. Okay? From the topological quantum field theory perspective, they are associating a representation on a vector space. Okay? And this vector space has to do, there's too much information here. But what's important is at the end of the day, they can relate, this is what they do in their paper, they relate Witten's approach to geometric quantization using a real polarization. That's what they do in this paper, so I encourage you to read that paper. But now I want to talk about the DACs. I'm here to talk about the DACs. So I need to first recall what is topological quantum field theory. So I need to talk about the category of vortices, and this is why, there we can quantize things that are all dimensional, okay? So remember the category of vortices, the objects are the boundaries, so n-1 dimensional closed manifolds, and the morphism, okay, are just the n-dimensional manifolds are just the vortices here. That's the morphism. And then we can compose adequately these vortices. And if we look and if we like categories, this is a monoidal category, okay? I want to thank now Jose Angel Prieto, because yesterday I asked him, please provide me with a slide with this summary in 1 page, and he did it. So thank you, Angel. And that is the category of vortices. And then the definition of, cooperate, okay. The definition of what is a topological quantum field theory, this is just a functor between the category of covortices and some vector space over a field, K, okay? And we require that this has some good properties that I'm not going to get into them. So essentially, topological quantum field theory, the idea of using the vortices comes in a way back to the idea of Feynman in his lectures on computation, where he was introducing the first definition of quantum computing, indeed, with the ideas of quantum field theory, because he was giving some algebra operation on the qubits. Okay, and this is the inspiration indeed for our work. We didn't start thinking of this in this categorical sense, but we came up with this categorical definition later. So now what I have to do is to introduce a new kind of topological quantum field theory. And what I'm going to do is to consider vortices, but I'm going to consider decorated vortices. So for instance, if I consider this vortice here, okay, I need, the decoration is given by a transverse vector field. This situation can also be seen in the paper of Lisa and Jonathan. They also had a transverse vector field in their business. So I'm going to define a topological quantum field theory that in the category of borders is decorated with some transverse vector field. And the transverse vector field, I'm going to explain the connection to the DAX now because it looks very strange. So I need to, indeed, this transverse vector field, what it does is it's going to put a dynamics in my problem, okay? And because the story of the DAX is a story that the DAX are lost and you cannot find them, indeed, the idea is that I want to associate a Turing machine to the DAX. I say, what is the connection of Turing machine with the DAX and the fact that you cannot find the DAX? And the answer was given by Alan Turing himself, and is the halting problem is an undecidable problem. That's the connection, okay? And you say, okay, what is the relation to topological quantum field theory? I'm going to add some dynamics in the cobordis, and this dynamics is going to be given by a geometry that in my case is going to be a contact geometry, and this vector field in the case of the DAX is going to be a rep vector field. So at the end of the day, this will allow me to quantize contact manifolds, but also to give not only a quantization of the manifold, but a quantization of the dynamics, okay? This is a bit abstract, but I just want to give some ideas. So that's exactly what I was saying, that Alan Turing in his thesis, he proved that the halting problem is undecidable. The halting problem was a classical problem to decide whether there would exist a supercomputer that could detect that any other computer on the world could stop with some particular input or not, okay? And this was a classical problem in the beginning of the 20th century, and all logical people were thinking of that. And he proved that the halting problem is undecidable, and he proved it by contradiction, trying to construct this supercomputer. And in doing so, he gave the definition of the Turing machine. That's what he gave. So what's important is that if I can associate to the movement of the trajectories of, in the case of the DAX, if to the trajectories of the DAX I can associate a Turing machine in a certain way, which I call Turing complete, that today I will not enter into that, then the conclusion is that there will be some fluid paths that are going to be undecidable. So this justifies that you cannot find all the rubber ducks. The rubber ducks, of course, is a metaphor. But this tells you that there are some fluid paths that you cannot find them. It's undecidable to find them. There is a logical obstruction. Okay. Now I have how many minutes? I have 8 minutes, right? 7 minutes, I can do it. Okay. Okay, so summary. What does Turing have to do with the rubber ducks and quantization? So just a summary. The simulator to find the rubber ducks could not find the rubber ducks. Only 2% of the messages on a bottle are recovered. So the question is, what if finding the rubber ducks is undecidable? Can we associate a Turing machine or supercomputer to the trajectories of the rubber ducks? And that's the connection to topological quantum field theory and to Feynman. Can this construction be considered as the basic unit of computation? Instead of qubit, I'm going to call it fluid, because it's done with the flow with a fluid. And then the idea is, can we use this computational model to improve maybe quantum computer? So the idea is, can we use topological quantum field theory? So what I will end my talk with is that there is a definition of topological quantum field theory, and there are many questions. But one thing we could understand is that this computes at time 1, always, our system. So in terms of time, it's much more efficient than the quantum computer. Okay, so the construction, and I'm going to go very quickly over this because I have 6 minutes now. The construction of this Turing machine builds up on another PhD thesis of Chris Moore, okay? This doesn't happen very often, that you do your thesis, and then people in the media talk about your thesis. That's what happened to Chris Moore. Chris Moore had proved that we can generalize the notion of shift in dynamical systems to something called generalized shifts, okay? And that this is equivalent to having a Turing machine. And so essentially what he proved is that the movement of a Turing machine, each step of the Turing machine, is the same as a mapping of the square Cantor set. How do you prove this? I'm going to try to convince you with some hand waving. Well, first, I'm talking about Turing machines. What is a Turing machine? Let's just think you have this idea of long tape full of 0 and 1s. And I want to think of the Turing machine as the printer. So it's a printer of states over this long tape, okay? And of course, there is a formal definition that I'm going to skip. But essentially, we have some instructions how this Turing machine is going to work. And this is called the transition function here. And here we have like a, here we have an example how it works. It changes 0 by 1s, and then it moves, the printer moves to the right, the tape moves to the left, and this corresponds to this +1 there. This +1 tells you how the tape has to move. So it's a very simple dynamical system. And okay, and I want to convince you that it's the same to advance on the Turing machine than a mapping of the square Cantor set, and this is very simple. We have the Turing machine there, and I have my camera, and I take a picture of the Turing machine, I do a snapshot. So I have a bunch of 0 and 1s on the left and on the right, okay? And I take these 0 and 1s as coefficients of the ternary span, okay? What does this give me? Because it's the coefficients of the ternary span, this is going to give me exactly points on the Cantor set. Okay, so X and Y are points on the Cantor set that I have constructed by taking the coefficients on the left and on the right. Therefore, this proves that it's the same to take a point on the square Cantor set than to take a picture of the Turing machine. Now, each time the Turing machine advances, this point is going to jump to another point on the square Cantor set. So this proves that it's equivalent to have mappings of the square Cantor set and the Turing machine, okay? And this is the idea of Moore, that this is the only idea that we used to do the following. Oh, well, I'm going to skip this. I'm going to skip this. There is the mathematics behind the movement, the way we model the movement of the fluids. If the fluids have viscosity, this is the Navier-Stokes equations, that you know there is a problem that is unsolved. This is why we started to think of this, because Terence Tao had asked if we could provide a Turing machine, we could associate a Turing machine to the Navier-Stokes equation. This is why we started to work on that. And we could do it in the case, in the Euler case, and we can also do it in the case of the Navier-Stokes, but I'm not going to talk about this. This is joint work with Soren Dir, who is connected, I think, and Angel and Daniel, okay? But in the Euler case, the way we do it comes from a very interesting coincidence, that stationary solutions of the equations that are called Euler equations are exactly red vector fields of some contact structure. So we use geometry for that. And with my former student Robert, Daniel Peralta Salas, and Francisco Presas, we proved that we could construct a solution of the Euler equations which is Turing complete, okay? This in particular gives the corollary that I wanted to explain, the ducts. There exist undecidable fluid particle paths, so there is no algorithm to decide whether a trajectory will enter a certain open set or not. So imagine that this open set is the neighborhood of the UK. There is no way to know this. And this is an application of the fact that the halting problem is undecidable. So in order to prove this, our construction, what it did was to, in a way, take the construction of Chris Moore, which was identify these Turing machines with mappings of the square Cantor set, take it from dimension 2 to dimension 3. And the way we did it is to look for a vector field whose time one map gives precisely that mapping. But, well, we had to extend the mapping. It's not exactly the mapping of Chris Moore. We had to extend it to a disk. And then we had to prove that there was a red vector field, which we did using the path method. Okay, this is how we prove it. And, well, the key point is that there is a correspondence. Oh, this is going too quick. Back here. So it's not cooperating. Okay. Enner and Grice prove that there is a correspondence between fluid dynamics and contact geometry in the following way. The solutions, stationary solution of the Euler equations that are there in the slides, but I didn't show you because it's like, doesn't make sense, and in the last minute I go to such details. But it's important that there is a correspondence between stationary solutions and red vector fields. And that's the kind of thing we use, so we use contact geometry to prove this. And what's next, and with this I finish. Come on. Okay. What's next is that, well, this construction, the connection to topological quantum field theory, is that our construction, the one that we did to prove that these fluid paths were undecidable, indeed can be drawn as a solution on just on a cylinder. So our idea is, okay, now I want to start playing with this cylinder, and for instance, to understand if I can see if I can do computations on a pair of punks. Okay? So our idea is, okay, let's take this construction we did as basic computation, and let's call it fluid, and then let's use topological quantum field theory to do a more sophisticated construction. This construction of the fluid answered the question of Terry Tau, but of course didn't give the blow up of the Navier-Stokes equation. However, we don't know if these other more sophisticated models can lead to the blow up of the Navier-Stokes equation. So the way we define this, our topological quantum field theory starts from the decorated the category of decorated cobordism, and it goes to the category of what is called partial recursive functions, because we need to compute, and this is a model of computation that was done by Klein. And the formal, what we proved, and with this I finish, this was quite intense talk, I'm sorry. What we constructed is what, my surprise. So what we constructed is, this doesn't cooperate with me. Come on. What we constructed is our topological quantum field theory. We call it topological Klein field theory, not because it's clean, but because it comes from Stephen Klein, who is the father of the model of computation, which is partial recursive functions, which is equivalent to Turing machines. But for us, it's convenient to present this model of computations. So what we proved, indeed, is that, okay, it was possible. The method to define this is essentially the following. You take the path. Imagine that you take a dynamics, a vector field that is Turing complete, and the way you define this computation is that you take the flow and you see where it goes out. But you may take, for instance, a dynamics very complicated. For instance, imagine that you have a plug, and maybe this point will never touch the upper part of the cylinder. But this is okay, because this is what people in computer science call a partial function. So if you have a plug, maybe your orbit is trapped here and it doesn't go up, but you have a way to define the computation. Okay? So this gives us a dictionary between dynamical systems and computational models that we know that this, in order for this to make sense, we need to have that this functor is full. And this is something we prove. So the theorem that we proved is that the functor is full. Therefore, it makes sense to talk about this topological Klein field theory. And this is a theory that we still need to explore to see if we could use this first like a model. This is like a hybrid computer between fluid and quantum. And it improves quantum computing time of computation. But we want to see what are the implications of this model. Of course, this is a quantization, indeed. But we want to understand the implications of this model. With that, I finish. Thank you very much. And happy birthday. Happy birthday.